Hello and welcome to this video on the relationship of surface area and volume of 3D shapes. We're going to be looking at kind of real world based situations and doing some modeling here with both surface area and volume. In past videos, we've talked about volume a lot, but in general, we're talking about surface area now is basically looking at each face or each side of a 3D shape of some kind, and then figuring out, well, what would be the total area if we found the area of all those sides added up together. And that's what we're going to kind of start with in the 3 or 4 parts of this lesson. So to start with, we're going to be trying to maximize area and relate it to something we've talked about before. It's just 2 dimensions right now. So we have a zoo that wants to give elephants as much space as possible in a rectangular enclosure meant for feeding. The zoo has a 180 feet of fencing, and they're trying to figure out, well, what would the maximum area be if we were to only basically have a perimeter, in this case, of 180 feet of fencing. That's what it means by fencing, is that you're basically looking at the area of that part of the enclosure. So I'm just going to take a second to pause the video here and think about what might the dimensions be that would maximize the volume if we were to do that here. So it turns out that there are a lot of options that you could use to do this. Like I could do, for instance, I could do 30 by 60. So that'd be, so we could do that over here. So 30 by 60 enclosure, well, that would be 30 plus 60 is 90, plus another 30 and another 60. So if I had a 30 by 60 foot enclosure, if I did 30 times 60, that would be 1,800 for my area, 1,800 square feet. So that's a pretty fair amount. So there are other options, though. You could also do a square enclosure, which would be 45 by 45. So that would just be 45 times 4 for the fencing. Well, that'd be 180 feet. So we had the right amounts. But 45 by 45 for area is going to be 2,025 square feet, which is a bigger amount. And it turns out that a lot of the times when you are looking at a maximized area, it is very likely that you would be looking for a square that would maximize the area if you had a certain set perimeter that you are working with. And that's something to maybe keep in mind as we go further into this lesson. So moving to part 2. So now we are thinking about the set of dimensions for a rectangular prism. We've talked about rectangular prisms quite a bit in this chapter so far. And we're going to try to see if we knew that the volume of a 60 cubic unit area, we want to try to see, well, what would be the possible surface area of the prism. And we're going to kind of make a chart here to do this, and then apply that to a real world situation as well. So if you want to pause the video there to determine what those answers might be, that would be something to do now. So now if you have given this some thought, you could start by making a table, because the dimensions themselves are not going to matter whether we're saying length, width, or height. We just have 3 dimensions for the volume of our prism. So I could make a table where I had x, y, and z for my 3 dimensions, and then I had the volume that I would get from them, and then the surface area from that. So if we just kind of think of an example of this would be a 2 by 3 by 10 for my dimensions. So the volume is what I want to have, 60 cubic units. So if I think about a 2 by 3 by 10 rectangular prism, so how you'd go about finding the surface area there is a kind of a different story. So if I have an example here, so I have a three-dimensional rectangular prism I've created here on the side. So I have maybe a 3 and then a 10 and then a 2 on the side there. So a lot of these dimensions, like these would all be 3s, and I can make my kind of interior dimensions that this would be a 3 in the back there. And then all of these ones along the bottom are going to be either 2 or 10. And so, for instance, from this one, I have kind of 4 faces that are going to be the equal to each other, kind of 1, 2, 3, 4 around the outside. And then the 2 ends, those are going to be equal to each other. So I have 2 of these end pieces. So they're both 2 by 3. So 2 times a 3 by 2 ends. And I'm going to add that to 4 of these side parts, which are all 10 by 3. So if I combine all these together, that would end up being my surface area. So grabbing a calculator, we can calculate that out. And it turns out that we have a surface area of 132. And that would be our, unless I miscalculated. No, I think that's right. So 132 would be my surface area there. So if I kind of fill out some more parts of my table, other options you could have are a 1 by 1 by 1 by a 6 volume or dimensions. And then I might have a 2 by 3 by 10 that I already have. I might also have a 1 by 6 by 10. I might also have a 2 by 5 by 6. All of these, if I multiply them together, would still get me a volume of 60, but they obviously all have a different surface area themselves. It turns out that if you were to calculate the surface areas of all of these, that our surface area of our 1 by 1 by 6 would give us the biggest of our surface areas. Because think about like one of those 6s right there, or by 60, I mean not 6. This is supposed to be a 60. That wouldn't equal 60. So now our volume would be 60. And it turns out that if we were to find the answer there, that you would have kind of a similar written out part here. So you have like 2 of these 1 by 1 squares that you'd be adding up. So it would be 2 and then 1 by 1, like that. And then you have basically a 1 by 60 face. So plus 4 of these 1 by 60 faces. And so that's like basically 2 plus 240. So that, if you compare to the one we found earlier, which was only 132, we found something that is a much larger surface area. And that kind of answers our question in number 2. If they're trying to maximize the contents of this battery, well, they want the biggest surface area possible because like the lithium that's inside of that battery is kind of folded up. Obviously, you wouldn't know this, but you definitely don't want to take apart a battery with all the acid inside, but just take my word for it that that's how it kind of ends up looking on the inside. And so they want to maximize the surface area, but the volume of the battery itself can't be any bigger because they still a AA battery has to be the size of a AA battery no matter what you're doing. The inside surface area is really what is going to matter for that particular topic. And so it turns out that when you have kind of longer, skinnier pieces like a 1 by 1 by 60 thing here, it turns out that those give you the biggest surface areas. And the larger dimensions you have, the kind of bigger sort of box-like shape you have, the smaller your surface area is going to end up being. And when you're talking about kind of manufacturing, sometimes when you have a larger surface area, that may not be the best. When you really want to be able to kind of minimize other things like making it maybe more user-friendly or fits into a case better. Like for instance, for comparing a sphere and a cylinder is going to kind of compare with a sphere because the cylinder uses less material generally, and also it kind of is easier to pack in something in a box as opposed to a sphere that might roll around everywhere with the flat sizes and whatnot. Okay, moving on to part 3. So in part 3, so we know that the volume of a sphere is, we've learned about that before, and it turns out the surface area of a sphere is 4 pi r squared, right there that I've circled. So if I want to do some quick calculation practice here, so the model, we're making a model of an elephant, obviously a very large animal with a sphere with a radius of 4.5 feet. So I could just do a little calculation review here by putting 4.5 feet into my volume formula. And if you grab your calculator and multiply that out, you get, if we're dealing with feet, 381.7 feet cubed. Surface area using our new formula would be 4 pi times 4.5 squared. And 4 pi times 4.5 squared equals 254.5 feet cubed. So similar to like an elephant, well, now we can model different animals using shapes we know. So obviously a snake is more like a cylinder, and it has a small diameter, and that's kind of what snakes are like. So if we think about comparing these together, so if we have 3 feet for the length of our cylinder, so our 3 feet volume, so we have volume is pi times our diameter is 0.2, so our radius is 0.1 squared, and then times our 3 feet in length. So pi times 0.1 squared times the length would be 0.094 feet cubed. Obviously a much smaller volume. Snakes are smaller. But then the surface area, we'll see how that compares. So when we're doing the surface area of a cylinder, that is basically going to be finding the area of the circle on the top and bottom and kind of doubling that first. So we have 2 times the area of the top. So diameter is 0.1. So 2 times pi times the radius squared. So we have 2 of these circle areas. And then we're going to be adding to that, which is basically when you think about a cylinder, if you find the circumference on the top and then multiply it by the height all the way down, that would be the surface area of the entire outside. So we would have the circumference 2 pi times our radius of 0.1, and then we're going to be multiplying that by the height, or the length in this case, of 3. And so that ends up all equaling, we can put all of that in our calculator together. And that is 1.948 feet squared for surface area. So let's compare these two animals, comparing the surface area to volume. So surface area of the elephant was 254.5 divided by 381.7. Doing that division, 254.5 divided by 381.7. So our surface area to volume ratio is about 2/3. So the volume is 2/3 that of which the surface area is 2/3 of the volume. But for the snake, we're going to have a different situation. If we're doing surface area is 1.948 for surface area divided by volume 0.094. You can tell where this is going. 1.948 divided by 0.094. That's 20.72. So we have an elephant that is much, much larger Well, when it's so big and kind of sphere-like in shape, generally speaking, obviously it's not actually a sphere. So that is 2-to-3 ratio of surface area to volume. Well, now we basically almost have a 20-to-1 ratio in this case, almost 21-to-1 ratio of surface area to volume. So we have a much better ratio comparing and a much larger kind of surface area kind of in comparison to the elephant from earlier. And that's a kind of what we wanted to look at there. Where you have kind of more cylinder shape. Well, that's going to have a higher surface area to volume ratio. A sphere is going to have a much lower surface area to volume ratio, comparing all of this together. Moving to activity number 4. So if we're going to look at kind of some different situations here. I know it's a lot of words to look at, so we're just going to look at it one at a time. So we have a human with a sphere with a radius of 1. So human, radius of 1. Ant is a sphere, the radius of 1/200. Elephant is sphere radius of 5. So in part 1, the raw strength of a living creature is the cross-sectional area of its muscles. The cross-section of each of our spherical beings is a circle of radius r, where r is the creature's radius. So now we're going to basically order the human, ant, and elephant by the raw strength from least to greatest. So we're going to basically find a circle area. Yeah. So a cross-section of a sphere is a circle. So first, our human is, we just have pi times 1 squared, so that's just pi. Our ant is pi. So pi is then times 1/200 squared. So that is going to be pi over, so 200 squared equals 40,000. So we have pi over the 4,000 squared. And so now that we kind of have that, so pi over 40,000 was our answer there. And so our elephant, we are going to be using a radius of 5. So pi times 5 squared would just be 25 pi. So relative strength is given by the ratio of raw strength to volume. It measures how strong a creature is for its size. Create an expression for the relative strength of a spherical being with radius r. Remember that the raw strength formula is pi r squared, and the volume formula for a sphere is 4/3 pi r cubed. So basically, just what we're doing here is that we are creating an expression for the relative strength of a spherical being. So we already did raw strength. So we're doing raw strength compared to volume. So we're just going to do raw strength of pi r squared divided by that. So we have pi r squared over 1 divided by 4 pi r cubed over 3. So we're dividing by a fraction there. And so we're going to flip that over and multiply. So we have now pi r squared over 1 times 3 over 4 pi r cubed. So our pi's in the top and bottom can cross out. So these two r squares, get rid of the 3 there, so we only have 1 r in the bottom, which means our formula here is going to end up being 3 over 4r. So we look at now ordering these in a list by strength. So the human we're going to use the radius of 1. So 3 over 4 times 1. So their relative strength is 3/4. Not too bad. An ant is next, so they're 1/20. So that would be 3/4 times 1/200. So putting that into our calculator, 3 divided by, in parentheses, 4 times 1/200. And that's 150 for an ant. And now an elephant is last with a 5. So 3/4 times 5. And that is just 3 divided by 20. So 3/20. So it turns out, based on the information we were given, that relative strength, kind of compared to like taking their size into comparison, is that we basically have figured out that a human is the middle, a elephant is the lowest, and an ant has the highest relative strength. And if you knew kind of about how that animal works, you would probably agree that that kind of makes sense based on what you have heard in the past. And lastly, we'll kind of read through some quick information and then wrap it up with a kind of exit ticket question that you guys are going to be working on in Google Classroom. So our question here asks, what other situations might involve surface area to volume ratios? Consider processes that happen on the surface of an object versus processes that happen inside an object. So something I mentioned before, so we have ice cubes of different shapes melt at different rates because melting happens on the surface instead of in the middle. A spherical ice cube, which you might have seen advertised in commercials for melting very slowly in drinks, that has the lowest surface area to volume ratio. So it is ideal if you don't want it to melt fast. And that's something to maybe think about when you're making ice cubes for any kind of large amount of stuff. So our lungs have many folds to increase the surface area for oxygen exchange. That same thing with our brains. Most of what our brain does is on the surface area. And that's why we have so many folds in our brain, is that most of the stuff we're doing is in those folds, and they want to have more surface area. And then also plants lose water vapor through their surfaces. When they live in hot areas, they have small leaves to minimize water loss. Think about like a cactus doesn't have any leaves at all. They're just those spines. Their spines on their skin are their quote unquote leaves, and they're basically almost losing no water at all, since those aren't even really leaves to begin with. But then if you think about like maple trees in like the north and Canada, those leaves are very large because they don't have to worry about losing water vapor through their surfaces. And lastly, you guys will be completing this exit ticket on Google Classroom instead of obviously doing it in the video. So you're going to be looking at each of these 3 prism shapes. They all have the same volume if you multiply all 3 dimensions. And we want to figure out which one has the least surface area and be able to kind of support that with reasoning. And that's something you will do in an exit ticket, as I mentioned. And that concludes our video on surface area and its comparison with volume. Thank you for watching.